Tamil?
Yes.
Good morning, everyone. Yeah. Today we are beginning the lecture on basics of classical mechanics. Now, basics of classical mechanics, we are going to have an overview what we have studied in our earlier collegiate time. Hello, can you hear me? Okay. Yeah, just a minute because there is some voice problem, connectivity problem. Just wait a minute. Yeah. Good morning, everyone. Now the voice quality is improved or not? I think I have changed the microphone and earphone and headphone. So I think the voice quality is a bit improved. Okay. Now, as we have already discussed in our first lecture, that we are going to have a teaching on particularly the distant learning through virtual platform. Myself will be teaching classical mechanics in CT1 paper, Core Theory 1 paper. And my partner is Dr. Piyush Solanki. He will be teaching mathematical physics. So we have a two component in this particular paper. One is classical mechanics. Second is the mathematical physics. Mathematical physics will be taught by Dr. Piyush Solanki. In this particular paper, we are having different units. So today we are starting with a basics of classical mechanics. You have already studied classical mechanics at TYBSc level. And you know many things regarding classical mechanics. But here we are going to have a very brief introduction of classical mechanics, what we have studied earlier. Today, we are not going to have a very big discussion, very big derivation, but we'll try to have an overview. Now, problem with classical mechanics and mathematical physics is that usually we do board teaching, blackboard teaching in a classroom. And there we have a freedom. But online teaching, we have to prepare PowerPoint presentation. And there are some limitations. Usually in a blackboard teaching, there is a factor of suspense because students don't know which equation is being derived or which step is after this particular step. But in PowerPoint presentation, student can see all the steps together. So the factor of suspense is not there. And sometimes it looks boring also. But we'll try to make it as much as interesting as possible. We'll try to share the PowerPoint presentation with you also later on so that leisurely you can see the PowerPoint slides. We'll also give you the links for online PDF books available. So you can download online books and you can read books at home. So there are two ways, PowerPoint presentation and downloading the books, textbooks and referring books. The PowerPoint presentation is usually prepared in a point-wise manner. and the textbooks are written in a different manner. So you have to use pen and notebook to write down some important points. And then you have to refer textbook, and then you have to combine both the things, because some things may be missing in the textbook. Those are discussed in PowerPoint presentation. For example, there are certain steps in the textbook that give direct results. But here we try to derive in between steps. So mathematical derivation is possible in PowerPoint presentation. So you have to use both the things so that you can make your notes complete. And now you have a ample time because you are learning from home itself. So you can refer those books, PowerPoint presentation leisurely. You can take benefit, maximum benefit of the time, and you can prepare your notes, prepare the subject in a detailed manner. Now, for any particular subject, we try to make it in a particularly the manner in which there are uh, there are two particular points. One, for any particular subject, there are three things available, and these things are related to philosophy, hypothesis, concept, logic, and tools and technique. Now, what is philosophy? We should not feel that it is a subject of arts, but here philosophy is related to science philosophy. In our particular case, in a mechanics, we have two different philosophies. One is Newtonian mechanics philosophy, another is quantum mechanics philosophy. And we have studied both the things at the TY level. So we know the philosophy difference between the Newtonian mechanics as well as in quantum mechanics. Then comes the hypothesis. Hypothesis in which there are certain assumptions made and there are certain concepts are used, and on that basis of hypothesis, people build up the theory. And then comes the logic. Logic is very important because without logic and without hypothesis and concept, logic is not important. And without logic, hypothesis and concepts are not important. So those things are related to each other. Now, why logic is important? Let me give you a very simple example. Right now, we have a winter season. So most of the time, people are wearing sweaters or woolen clothing. But if somebody is feeling warm, right now, the climate is a bit warm. So you don't require to wear sweater. But sometimes people wear t-shirts also. So there is a logic that climate is not so much cold, so we can wear t-shirt. But if climate is cold, then we have to wear sweater. But if somebody comes with a raincoat, then we'll laugh. Raincoat is not at all required in a winter. It is not logical also. If somebody wears raincoat in a winter season, it's not logical, and people would laugh at that particular person. So logic is that it can be explained with some reason. And that is why logic is very important in particular theory. Then last one comes the tools and techniques. For any particular theory, we have to use tools and techniques. And in classical mechanics, the tools and techniques are mathematics based, and particularly the calculus based. So we have a particular sequence. In that particular sequence, first comes philosophy. Our base is Newtonian mechanics, Newtonian philosophy. Then comes the hypothesis. We have to assume many things. Then we have to make it more clarified. Then concept comes. Then we have to make our argument more logical one. Then logic comes. And ultimately, we have to apply tools and techniques. Here, the calculus or mathematics is considered as a tool or a technique. So classical mechanics is based on calculus. And calculus we have already studied in mathematics. Now this topic is very, very interesting one. And in mathematics, people call it applied mathematics. In physics, we call it classical mechanics. The same topics are being covered in mathematics, but there they call it applied mathematics. Same textbook, Goldstein, is being followed in mathematics, but their approach is different. In our case, our approach is different. Now we have already studied few things like generalized coordinates and configuration space. We know that the term generalized coordinates refer to the parameters that describe the configuration of the system relative to some reference configuration. And these parameters must uniquely define configuration of the system relative to the reference configuration. And this is done by assuming, this is done by assuming that this can be done with single chart. And we know that the generalized coordinates and generalized velocities are defined. So configuration space is dealt with the generalized coordinate system. And we have already mentioned that Q1, Q2, Q3 up to Qn or Qi are representing generalized coordinate system. Those can be converted into any coordinate system like Cartesian coordinate system, spherical polar coordinate system, or any other type of coordinate system that can be converted. Then configuration space. In classical mechanics, the parameters that define the configuration of a system are called generalized coordinates, and the vector space defined by these coordinates is known as a configuration space in a physical system. Now, there are two types of definitions available. If you look into Wikipedia, they have mentioned that there are two types of definition available. This definition is from physics point of view, that vector space defined by these coordinates is called configuration space of the physical system. So here the configuration space is defined by Q1, Q2, Q3, all the coordinates. Now, in mathematics, it is defined in a different manner. Suppose we imagine that there are n particles and n particles are to be represented in 3 dimensions. So one particle requires 3 coordinates like that. N particles are there. So 3n different coordinates are required to describe the n particle system. In mathematics, they consider that instead of considering n particles moving in a 3-dimensional system, one particle is moving in a 3n dimensional coordinate system. So they define that configuration space in a different manner. But we are bothered about the configuration space so far as it is considered for the physics point of view. Now we come to the phase space. We have already studied the phase space. Now what is phase space? And you can see the 3 photographs of a famous scientist. One is Ludwig Boltzmann. We know that Boltzmann constant is particularly the creation of a Ludwig Boltzmann. Another one is Henri Poincaré. You can laugh at the spelling of that particular scientist name. It is pronounced usually Henri Poincaré, but he is a French scientist, or he was a French scientist. And in French language, the pronunciations are different from normal English pronunciation. So it is not pronounced as Henri Poincaré, but it is pronounced as Henri Poincaré. So slightly different from normal English pronunciation. And the last one is Josiah Willard Gibbs, American scientist, American mathematician. He contributed in developing the phase space. So one is German, another is French one, and the last one is American one. So 3 great scientists, they have contributed in developing the phase space. Now, the French language is a sweet language. And I mentioned about the name of a scientist. It is not pronounced as we pronounce in our normal English language, but it is pronounced in a different language or different manner. Now, let me share one funny incident that took place in my life. Nearly 15 years back, I had to visit France. So I wanted to attend one conference in one city. So I went there, And I check into the hotel, and there the room numbers are given, but they write chamber. Chamber number 1, chamber number 2, chamber number 3. And same thing in English, that we call room as a chamber. But they pronounce in a different manner. Instead of chamber, they pronounce as chamber, not chamber, chamber. So I landed at that hotel very late night. I was hungry. And when the receptionist told me that chamber 12, so I thought it is something like a sambar. But I was hungry. So I was just feeling that it should be something like eatable. But when he gave me the key and I found that it is the chamber, it is not something else. Now, these three scientists, they contributed in developing this phase space. Now, in dynamical system or dynamical theory, the phase space is a space in which all possible states of a system are represented, with each possible state corresponding to one unique point in the phase space. So dynamical system is having a momentum, is having a coordinate. So that particular dynamical system is represented by unique point in a phase space. And we know that in a phase space, one coordinate axis is momentum, another coordinate axis is coordinate or generalized coordinate. So x-axis is momentum, y-axis is a coordinate or generalized coordinate. So phase space is represented like that. And for mechanical system, the phase space usually consists of all possible values of position and momentum variables. So that particular point represents the possible values of position and momentum. And large number of points describe the large number of positions of different particles and different momentum values. So phase space is a concept which was developed by Ludwig Boltzmann, Henri Poincaré, and Joshua Willard Gibbs. Now we come to the Lagrangian equations. Again, French mathematician Lagrange, he gave this particular concept of Lagrangian mechanics. Now, again, the photograph of Lagrange is shown here. We have already studied in T by BSc the Lagrangian. The Lagrangian is represented as L. It is equal to T, the kinetic energy, minus potential energy. So Lagrangian is represented as the kinetic energy minus potential energy. And also it is represented as L equal to L function of Q dot nt. And we know very well that the Q is generalized coordinate and Q dot is the generalized velocity and T is time. So Lagrangian is represented as L is equal to T minus V, and also it is a function of Q dot nt. Then we have written here the Lagrange equation of motion. So it is represented as d by dt and del L by del Q dot I and minus del L minus del Qi is equal to 0. This is also known as Euler-Lagrange equation. Usually it is known as Lagrange equation, but it is known as Euler-Lagrangian equation also. The beauty of this equation is there are n different equations because I represents 1 to n. So I can be 1, I can be 2, I can be 3, up to n. So there are different n coordinates in a system, and each one representing one equation. So there are n different equations, and there is a double differentiation. So it is a n second order differential equations. Then we come to another concept, the canonical variables. Now canonical variables are represented by Q and P. Q is the position coordinate and P is the momentum. And that is represented usually in a bracket form. So that represents the canonical variable. Now canonical variable can be equated by canonical equation. So equation is shown as minus Pi is equal to del L function of Qi, Q dot I and T by delta q dot I. So that shows the canonical relation. Now, why it is known as a canonical relation? Because canonical variables q and p are related to each other through Lagrangian function. So these are known as canonical variable. So here we can see very easily that pi is related to q dot I through Lagrangian function. So Lagrangian function connects these two, and that is why this is known as a canonical equation, and these are known as canonical variables. Now, Lagrangian function is in the configuration space because we know that only q is there, q dot is there, time is there, but momentum is not there. So that is why the Lagrangian equations are formed in configuration space. Now we come to one more thing, the Hamiltonian equations. Now, Hamiltonian mechanics was first formulated by Irish mathematicians. You will hear all the names of mathematicians. Basically, they are mathematicians, but they have contributed in physics. So their treatment of a problem is via mathematics and particularly through calculus. So Irish mathematician formulated this Hamilton's equation in 1833. And he started using Lagrangian mechanics, and Lagrangian mechanics formulations were modified by him. Now we know very well that in TYPSC we have studied Hamiltonian. H is function of Q, P, and T. Now phase space comes here. In Lagrangian equation, it was Q, Q dot, and T. Q, Q dot, and T. Here, Hamiltonian is function of Q, P, and T. Now, Q dot is not there, only P is there. And that is why it is very easy and suitable to use phase space concept, because we have a Q, we have a P, and we can represent this by a phase space. We also know that the Hamiltonian can be represented as T plus V, where T is the kinetic energy and V is the potential energy. You can remember that the Lagrangian was represented as T minus V. There is a slight difference between Lagrangian and Hamiltonian. Hamilton was a well-known mathematician from Ireland, and he contributed a lot in classical mechanics. We'll learn many things, many topics in classical mechanics which are contributed by Hamilton. So Hamilton's name is associated with many formulations in classical mechanics. Hamiltonian is so important that it is dealing with the total energy of a system. It is the summation of kinetic energy plus potential energy. So Hamiltonian is very important in quantum mechanics also. And that you have already studied in TYPSC, that Hamiltonian is written in quantum mechanics also. So Hamiltonian is such a function that is important in classical mechanics as well as in quantum mechanics. Now we come to the Hamilton's equation of motion, and Hamiltonian is represented as H function of Q, P, and T. These are the Hamilton's canonical equation of motion. Why canonical equation of motion? Because we have already seen the Lagrangian equation. There we had already seen that momentum and coordinate are connected through Lagrangian. Here, the momentum and coordinate are connected through Hamiltonian. So there are two different equations. These are known as the Hamilton's canonical equations, because there the coordinate and momentum are connected with each other. Here, the coordinate and momentum are connected with each other. Now, there are two different equations, and these two different equations are 2 and first order partial differential equations. These are not full differential equation, but partial differential equations. There is a small corrections here, qi, but it is actually q dot I, and in this dot is shifted to here due to the conversion into the PowerPoint. So just have a correction that p dot is okay, but a q dot is shifted on the right hand side on the top of p. Actually, it should be on q dot I. So just have a small correction. So you will notice that here there are two different equations. One equation is having a plus sign, another equation is having a minus sign. And these equations are I is from 1 to n. So n different equations. Again, these are also n different equations. So there are 2n first order partial differential equations. Lagrangian equation was second order differential equation because double derivatives were there. But it was having only n equations. Here the number of equation becomes double. But those are partial derivatives and first order, not second order. So we have a benefit sometimes in Lagrangian equation, and we have a benefit sometimes in Hamilton's canonical equation. So depending upon the benefit, we can use either Lagrangian equations or Hamilton's equations of motion. Now we come to the another interesting part, that is the Hamilton's principle. Now Hamilton's principle in mathematical manner, it is represented in a different way. But we'll try to understand the concept here, that why Hamilton's principle is very important and we'll be using quite often in classical mechanics. Now we have considered over here one diagram. And in that diagram, we have represented Qi and Ti. And another one is Q2, T2. So one is Q1, T1. Another is Q2, T2. And there are connections between these two different points. So one is the shortest one that is represented by red line, and others are different paths. So there are different paths connecting these two different points. And some paths are very funny and very long paths. So again, these funny and long paths are again connecting the two different points. But the idea is the red one is the shortest one. And these other two are shorter, but not shortest one. And these are the lengthier one, because we can see even by looking at the diagram that the paths are very lengthy, very long one, and many curves and other things are there. But the red path is the shortest one, and neighboring paths are again shorter, but not the shortest one. So we want to find out that which one is the shortest one and which one is the longest one. Now let us see the particularly the things what is written here. We know that as the system evolves, the Q traces a path through configuration space. So the system is changing with time. So here Q1, T1 and Q2, T2. So the system moves with time. And the path taken by the system, that is a red line, has a stationary action. And delta S is equal to 0. And under the small changes, the configuration of system is delta Q. Now, what is the meaning of stationary and why delta S is equal to 0? Now, in a box, the meaning is given. This is known as a stationary. Stationary means maximum or minimum or at a saddle point where derivative of a function is 0. When derivative of a function is 0, it indicates three things. One, it is a minimum. Another, maximum or a stationary saddle point. And at that time, the function is not changing. Not changing means constant. And if you take a derivative, any material or any function which is having a constant quantity, and if you take a derivative, it is 0. So any function which is a constant one, not changing at all, then derivative is 0. But if function is varying, function f of x is varying, then derivative is possible. But fx is not varying, is equal to constant, then if you take a derivative, any constant quantity, differentiation is 0. So any particular quantity, the differentiation is 0, then it is a constant or stationary. And here the constant means either it is having a minimum value or maximum value or at a saddle point. Now it indicates the three things, and that is represented by a particular line. Now let us come to another example. Now there are bunch of sticks available here. You can see in the photograph, bunch of sticks available. Now the question is given, Hamilton's principle and finding the minimum or maximum length of a stick. Now we have to find out which stick is the minimum, which stick is maximum. So what we do, we take one stick and we try to compare with other one. And like that, we'll come to a particular stick, which is the shortest one. And shortest one, you cannot compare with any other stick, because if you compare with the other one, still difference is there. So if you compare the shortest stick with itself, then difference is zero. But if you try to compare the shortest stick with other stick, difference will come. So difference becomes zero when the shortest stick is compared with itself. And that indicates that we have reached the shortest stick. Similarly, we want to identify the largest or longest stick. Again, we try to compare one stick comparing with another one, and we try to find out difference is there. But when we come to a last stick and difference is also found, but then no stick is left, then we have to compare the same stick with itself only, and difference becomes zero. So that indicates that we have reached the largest or longest stick. So that indicates that if you try to compare with itself at the end of the process, then difference is zero. But if you try to compare with other one, difference is always there. So that indicates that you have reached the longest stick or shortest stick. So similarly, in the previous slide, we have seen that this is the shortest distance that can be identified with taking a difference with the neighboring one. If you take a difference with the neighboring one, the shortest one is the least one. The neighboring one is slightly longer one, difference is given. Even this neighboring one, it looks similar to the shortest one, but difference is given. But ultimately, when we try to compare the shortest one with itself only, then you will find no difference. And that shows that we have come to the shortest path. So that is represented by Hamilton's principle. Now, Hamilton's principle, the motion is such that the variation of line integral from one fixed point t1 to t2 is zero. So that line integral is delta I, and it is represented as del or delta. Line integral is from t1 to t2, and of a Lagrangian is zero. And again, we go back. If we try to write a Lagrangian for this one, if we try to write Lagrangian for this one, it is showing a line integral. Line integral is from t1 to t2, and for a shortest path, the line integral difference that is represented by delta is zero, and that shows that it is a stationary value. Stationary value here, it is the shortest one, or in other case we can consider longest one, but here we consider the shortest one, and the variation becomes zero, and it is having a stationary value. Now I come to the last part, and that is we are using two different textbooks. One is Classical Mechanics by Goldstein. Another one is Classical Mechanics by Takwal and Puranik. So these two books we'll be using. I have already downloaded Classical Mechanics by Goldstein, and I can share with you people that you can refer Classical Mechanics by Goldstein. Now, Classical Mechanics Goldstein is an international standard book. And if you go to any university in India, the classical mechanics is taught from Goldstein. It is one of the textbooks. There are many other reference books also, but in majority of universities in India, even in foreign countries, if you go to USA, UK, or any other Western countries, the classical mechanics is taught by the book from Goldstein. So Goldstein is a very standard international book, but the language is tough. So many times students, they refer classical mechanics by Takwal and Puranik. Takwal and Puranik is written on the basis of classical mechanics by Herbert Goldstein, but the language is much more simple, and it is digestible to our students. So two books are there. The standard book is Classical Mechanics by Goldstein. Another book is Classical Mechanics by Takwal and Puranik. Goldstein was a very noted scientist, and I just give you one incident of Herbert Goldstein. You have heard the name of Richard Feynman. And you must have remembered that Richard Feynman coined the word nanotechnology. He was a Nobel Prize winner, and he was a dedicated scientist. His contribution is well known. So once he was sick and he was detected cancer, so he was hospitalized in USA, and he was to be operated. Goldstein was his friend, so he visited him in the hospital the previous day evening. So next day operation was to take place. So they discussed one problem, mathematical problem, and they started deriving equations. And ultimately they could not find solution. So ultimately Goldstein got tired and he said, I will go home. And once you recover from your cancer treatment and the operation is successfully completed, we'll try to solve this problem. So he came at home, and before sleeping, the phone call came, and that was from Richard Feynman. So Richard Feynman was on the phone. He said, Goldstein, we were busy in solving a problem, and we were breaking our head, but we could not solve the problem. But after you left, I just worked on that further, and I got the solution. And I have written on a piece of a paper you can collect from my hospital when my operation is going on. So that was the dedication of a scientist. That next day, very major operation was to take place, but even he was working on a mathematical problem or a physical problem and wanted to solve the equation through mathematics. So these are the dedication of a scientist who have contributed a lot. Now, let me add a few things. Classical mechanics and quantum mechanics are highly philosophical one. In my slide, I have mentioned about the first part is a philosophical one. So philosophical one means requires some visualization. Why visualization and concept? Because many things we cannot observe directly. For example, the phase space. We can observe three-dimensional Cartesian space, but we cannot observe phase space. And all these equations are written in a phase space. So many conceptual visualization is required. And here in classical mechanics, I request all the students to read textbooks. It is not the subject to be mugged up. If you mug up, you will get marks, but you will not understand the subject. In classical mechanics and quantum mechanics, visualization, understanding the philosophy, understanding the logic is very important. Why we are doing like this? It is to be understood. So here we have completed our first introductory lecture, and thank you very much for patient hearing. From the next lecture onwards, we'll start our regular teaching, and that will be beginning with the canonical transformation. I will go slowly. I will share you after the lecture, after completing the topic, I will share the PPT so you can read at your leisure, and you can try to understand this. We'll have a separate lecture for interaction and doubt solving, because if we try to solve doubt, we will not concentrate on the lecture. So plus my request is first try to listen the lecture, try to observe PowerPoint presentation. Whenever I share the PowerPoint presentation at home, again, you try to see leisurely the PowerPoint presentation, note down your doubts, and we'll have a doubt solving session where we can discuss about the doubts. Because if we try to discuss doubts in between, we're not able to complete the topic. And if the continuity is lost, again, it is very difficult to understand that what we learned earlier and what we are going to be learned after some time. So the continuity is broken. So if we try to discuss about the doubt solving, so we'll have a separate session for doubt solving. So once again, thank you very much. And thank you very much for your patient hearing. And this time we are not marking any presence, but in the next lecture, we'll try to mark the presence. And thank you so much. Thank you.